First of all, thanks to the organizer for inviting me, I guess. So you already have a couple of lectures from Manuel and Elisa talking about black hole binaries from galactic, from dense environment, and Elisa treated all the part about dynamics. So for the 3 hours that you still have to attend this school, we will discuss about massive black hole, basically. This time I will do it mostly at the blackboard. So if I write something that is not clear, please let me know. Also, it's my first time giving a lecture at a school, so if I say something that is not clear, or like if a concept is not clear, feel free to ask. So just a couple of references before we start. Thank you. So I use a couple of reviews to produce these lectures. So first one is this archive number that comes from a set of lectures that a couple of PhD wrote after some lecture given by Alberto Cesana. And the second review is something quite recent, done by Marta Volonteri, that actually came out last week. So, okay, so with that we can start. And we start talking about how we form massive black hole. So the original idea comes from Riss. It was like an historical paper in 1978, and the idea is relatively simple. So the idea is that if you have a gas cloud, you have a balance between the pressure that of course is trying to push and to expand the cloud, but on the other side you have the gravitational force that is trying to compress the cloud. And basically, depending on the typical mass of these clouds, you can have different formation channels. Before talking about the different formation channels, I will derive some limit, basically some conditions that are used typically to establish the collapse or not. By the way, I know that you come from very different background, and astrophysics can be a bit unwavering. So if maybe you are working on TDI or waveform, maybe you are used to something very accurate and precise. Astrophysics maybe is not exactly falling in this category. Okay. So let's start with one of the concepts that is mostly used in astrophysics, that is the condition that is called the Jeans mass. So this condition basically describes the condition for collapse. Assuming balance between pressure and gravity. So in order to get this condition, we can start from a theorem that is used often in astrophysics, that is the virial theorem. So I don't know if you are familiar with that, but the idea of the virial theorem is that you can basically write that the 2 times the kinetic energy plus the potential energy is equal to 0. By the way, if I write too small, again, from the background, like raise your voice, okay. And this condition is typically applied for a stable and gravitationally bound system. So in this case, what we are considering is basically a cloud of molecular hydrogen. And as you can imagine, well, kinetic energy tries to expand the cloud, potential energy is trying to make it collapsing. So the condition for collapse is basically that the potential energy is larger than the kinetic one. So if we take a self-gravitating sphere of radius r, you can write the potential energy as integral from 0 to the radius of the sphere of 4 pi r squared, density, and dr. And assuming, again, we are assuming a sphere, so we just have that the total mass is this quantity, and if you just do the substitution, you end up with an expression that looks like minus 16 over 15 pi squared g rho squared r to the 5. On the other side, we also have the kinetic energy. So in this case, the kinetic energy can be written as 3 over 2, the total number of particles that you have in the cloud, times the Boltzmann constant for the temperature. And I'm going to rewrite this as 3 over 2, total mass, the mu, in this case mu is the mean molecular weight, times the mass of the hydrogen, and then again, Boltzmann constant, temperature. And at this point, you just have to compare these two, and again, we can use the relation that the radius is basically proportional to the mass. And if you do that, and if you apply the condition that has to be larger than, okay.
Question.
Sorry, yeah.
Okay, thank you. I didn't understand how you went from the virial theorem equality to the inequality.
Because the idea is that the equality is when you have stability.
Okay.
Here you want to see the condition for collapse. And collapse is not stability.
Okay.
So that's why I went from the equality to the inequality, because I want to see when the non-stability, so in this case the collapse, take over.
So there is not enough kinetic energy.
Exactly.
Okay. And that one after capital G in the second line is a rho or an E? No, in the second line.
Which one?
In the second line, after you solve the
16
integral.
by 15.
Rho is
Yeah,
not a
density.
function of R. Okay.
There's no eccentricity
But it's not a function of Isn't rho a function of R, of the distance from the center?
Exactly. This is the case of a uniform. So the density does not depend on R.
Okay.
Okay. So if you do the inequality, you end up with the condition that M should be larger than 5 Boltzmann constant, temperature over G mu, mass of the hydrogen, 3 over 2, and then, well, some numerical factor. And this is what we define as Jeans mass. If you rewrite this in more useful quantity, let's say, you end up with Jeans mass that is 500 times temperature over normalized at 200 Kelvin to the power of 3 over 2. Gas density, again, in this case normalized to 10 to the 4 centimeter cube to the power of 1 over 2 times solar mass. So basically, when your cloud is larger than this Jeans mass, first order approximation, you have collapse. So the idea is that depending on the type of halos that you consider, you might have different type of collapse. Just to give you an idea, for example, if you want to use this scaling relation, here we are looking at the temperature of, as I said, molecular hydrogen, because that's what collapse and form stars. So, for example, if you want to have a rough estimate, this temperature for something that is today, so at redshift 0, the temperature of star-forming molecular hydrogen is at the order of 10, 20 Kelvin. So if you just do the math, you see that you end up forming stars that are relatively light, let's say. But of course, if this temperature increase, and of course also if the density of the gas increase, you might end up forming stars that are a bit too massive. And that actually brings us to one of the first proposed formation for massive black hole. So I guess you are familiar more or less with the cosmological picture. So you have, okay. So with the cosmological picture, in the sense that you have dark matter halos that are like around the universe, that indeed are made of dark matter, and then you have ordinary matter that start falling into it. So one of the proposed formation channels is what people typically call POP3 stars.
Can I ask a quick question?
Yes.
Just, I guess this can be rewritten with metallicity, right? Because with the metallicity term instead.
So metallicity play a role, of course, as I will discuss it briefly. But in principle, yes, you can write it. So in this case, I'm not writing with metallicity because the idea is that we use this at high redshift just to form the first black hole. So I'm assuming basically zero metallicity. So what you have is basically what comes after the Big Bang nucleosynthesis, so mostly hydrogen.
Okay.
But in principle, yes, it's a function.
And it'll come as whatever MH is. It'll be the fraction of hydrogen gas, basically.
Yes. So one of the proposed formation channel is what people typically call POP3 stars. These has also been called typically light seeds and tends to produce a black hole of the order of 10 1,000 solar mass. So the idea is here is that we have what we typically call mini halos. By the way, astrophysician likes nomenclature. So you will see that there are people tend to call the same things with different name. I will try to be as clear as possible, but if that is not clear, please ask, of course. We have typically, in this case, the idea is that we have mini halos that are dark matter halos with typical mass of the order of 10 to the 5, 10 to the 6 solar mass in terms of dark matter, okay, just to clarify. And the idea is simple. So you have some amount of hydrogen, and in this case, the temperature of the molecular hydrogen is at the order of 200 Kelvin, basically. And this brings you to basically creating stars that have a very large mass originally, so already at the beginning. There is also a couple of considerations about metallicity. So the idea is that metallicity plays a couple of roles in determining the fate of a star. First, it has been observed that if you have some metals in your molecular hydrogen cloud, this favors fragmentation. So basically, the idea is that fragmentation leads you to the formation of stars that are not as massive as what you would like to have to produce seeds. So imagine that you have your big cloud of molecular hydrogen. You want all of this to collapse, basically, in order to form a single POP3 stars. But if you have metals can cool the gas quite efficiently. So you end up forming like small region of star formation. So at the end, all this mass is not converted in a single stars, but in smaller stars. cube. Okay.
Sorry, I think as not, but just to be, so you're saying these mini halos are the ones forming the population 3 stars?
Yes.
Okay, great, thank you.
And the second role played by metallicity is instead towards the end of the life of a star. And the idea is that typically if you have a star that has a lot of metal, at the end of the phase, metals can push away the outer envelope of hydrogen, which means that at the end, the black hole that you form is way less massive than the original star. While instead, for stars with a very low metallicity, you end up having more or less kind of linear relation between the mass of the star and the mass of the final black hole that you produce. Okay. By the way, I forgot to say something. So I derived the Jeans mass in this way. That is an approximate way. If you want to do it in a, let's say, a bit proper way, you basically have to take the continuity equation and you have to take your Euler equation. You end up with a set of differential equations. You perturb them to see what happens if you are outside stability, and you do all the calculation, and at the end you end up with an expression that is very similar. Okay. So the second possibility to form, maybe here I can just squeeze. Yeah. Go.
Could you elaborate on, you said that the higher metallicity gas helps cool it more effectively, the higher metallicities work.
Yes.
Can you elaborate how? Is it like a cross-section area thing, or is it
yes.
just more massive, so less velocity or something like that?
I think the idea is that you have something that is a bit more massive, so you have less kinetic energy and it's easier to collapse, basically. And also radiation can escape easier in case. Because it's radiation what also is giving you some push. So there are a couple of other formation channels. So one, I think, is the one that Manuel already mentioned to you. It's what typically people call runaway cluster mergers. Again, in terms of nomenclature, people like to call these as medium weight seeds, and these are expected to produce a black hole of the order of 10 to the 3, 10 to the 4 solar mass. I'm not going to say a lot about this because I think it is exactly what Manuel already told you. So the idea is that these things create in clusters, so you have a lot of interaction. So maybe you start with something that is relatively light, but then due to the dynamical interaction between black hole and stars, you end up building things that are way and more and more massive. The third possibility is, well, as you can imagine, what people call heavy seed. So the third scenario is typically referred to as direct collapse, and it is indeed what people call heavy seeds. And in this case, you end up producing black hole of 10 to the 4, 10 to the 6 solar mass. So the idea is that if you want to produce this type of seed, you don't want star formation to happen, basically. Because if star formation happens, you end up forming puppetry stars, of course. So in this case, you don't want a star formation to happen. And this can be, let's say, achieved in two different ways. So the first one is that you might have what is called UV radiation. In the Lyman-Vermeer band. So this UV radiation is typically made up of photon with energy between 11.2, what is it? is between 11.2 and 13.6 electron volt. And the idea is that this UV radiation is sufficiently strong to photodissociate any molecular hydrogen that you have. And as we said, basically the molecular hydrogen is a way to cool down your gas. So if you have a lot of this like UV radiation, you don't cool it down, so you prevent the fragmentation and you don't end up forming POP3 stars.
What is photodissociate?
You have no, it's fine. So you have the molecular hydrogen, it's just hit by a photon, and the photon just give enough energy to the molecular hydrogen to split. So and then you end up with hydrogen and hydrogen. So this is one of the proposed mechanisms. Typically, UV. What?
Where does the UV radiation come from?
Exactly. So that's what I'm going to say. Exactly. So the point is that UV radiation, should be sufficiently strong, of course, to make this effect relevant. And there have been several ways to, let's say, come up with the possibility of UV radiation, because like the UV radiation, the background UV radiation that you have from CMB, that is way too low to basically have a significant effect. So one idea is the possibility of some sort of combination between light and heavy seeds. So the idea is that you have the first POP3 stars that collapse. These produce UV radiation, and then the UV radiation prevents the bigger halos to collapse because they give them this sort of UV radiation. Another possibility that has been proposed, but I think it's now a bit, let's say, abandoned, is what typically people have called synchronized halos. The idea is that here you have two massive halos that are, let's say, close to each other, and the idea is that one of the two just go collapsing slightly before the first one. And in this case, if like one collapses before the first one, it can provide the UV radiation to support basically the other one. The problem with this approach is basically that you need a very fine tuning between the two halos. So I think after just few mega years, basically, if you start this at time t0, just after a few mega years, you should also have the collapse of this one. So it's very ad hoc, let's say, and you really need to fine tune your parameter. Another possibility is, in order to have such a big inflow, is what typically people have called, again, dynamical heating. So here the idea is that you don't have any more UV radiation, but you have that halos grows rapidly in mass. So the idea is that in this case, you don't think anymore to the standard picture of a sphere. Maybe you have inflows of gas coming from different directions, and this can help you basically getting something that is very massive, then at the end collapse. Okay, let me check if I said everything. Okay, fine. There are a couple of other ways to form seed black hole. I'm going to mention them, though they are not strictly related to astrophysics. And one possibility is primordial black hole. Primordial black hole basically span a very broad range in masses. They go from 1 gram basically to 10 to the 5 solar masses. There are several constraints on the relative abundance. There are several constraints that comes from the CMB, for example. So the idea is that you know that if you look at the CMB and if you look at the different multiples, you end up having the usual curve. The point is that, of course, if you have things that start accreting the radiation on the CMB, this picture is perturbed. So you can get some constraint on the abundance of primordial black hole from CMB. Another possibility is that you can look at globular clusters. Globular clusters are just clusters of stars. And the idea is that if you have some primordial black hole going around, at some point it will interact with the globular cluster, so something should happen, like accretion. And you can also get some constraint on them, just looking at the typical X-ray background. So the typical X-ray background that is produced by the black hole that comes from, let's say, astrophysical channels. You can compare it with what you would expect from a population of primordial black hole, and in that case, you can put upper limits on the population of primordial black hole. The other possibility that again has been used in that has been proposed in the literature is cosmic strings. Here I have to confess that I have question marks even on my note. So as far as I understood, they are like consequence of string theory, and somehow they can accrete matter. Don't ask me more. Okay. But I mean, I just give you this information. If you want to know more about that, for example, there is some references in the review of Marta Volonteri, so the second reference that I give you. Okay. Final consideration about this is that people typically have considered the different formation channels as somewhat separate, in the sense that I think we have seen that basically when you need to simulate when you want to perform a cosmological simulation, you have several different scales. So the scales of the black hole and the scales of the globular cluster is way much different and is way much smaller than the scale of like a dark matter halos. So both due to personal interest and also due to the limitation of like simulation, people have typically looked at formation channels in kind of separate way. So people focusing just on light, medium, or heavy seeds. Nature is probably continuous, okay? So it's difficult that what will happen at the end is like a clear distinction between three different models. And what we expect to see with LISA is, of course, some combination of these formation channels. As you can imagine, at this moment, it's not really we can get a lot of constraint about this seed black hole because, they're at very high redshift. They are typically low mass. So let's say that really one of the objectives of LISA is indeed to understand how black hole form and basically what is like, I mean, maybe there is going to be a main formation channel, but basically to have an idea of the different combination, how they interact with each other, and what is the relevant fraction. Okay.
It looks to me that only the medium weight seeds would apply for lower redshifts, because the others seem to be very early universe scenarios. Is that wrong? Direct collapse, primordial black holes, POP3?
In principle, yes, but I would say that it depends a bit more on the property of the cluster. The point of the cluster is that the moment you put dynamic, you typically end up with something that takes a lot of time. And yes, in principle, as you said, it's not really anymore like early universe. So it's not something at redshift 20. Because at redshift 20, you didn't have enough time, basically, to do that. I think that if you look in the literature, you can find some maybe ad hoc simulation where if you put like enough mass in your cluster, you might have some very rapid collapse.
What if we flip it around and I ask you, what is the formation mechanisms for IMPH and above in the nearby universe? Then you would say it's probably runaway cluster, right? You wouldn't say POP3. You wouldn't say direct collapse.
Why not? I mean, in principle, you can start with something at 10 to the 3 solar masses. Maybe it's in a galaxy with low gas. That may happen. And in that case, it's not accreting a lot of gas. So at the end, at redshift 0, or wherever we are going to observe it with Einstein telescope, more like a light seed, it's going to be at redshift 2 or 3. You also have to take into account that I mean, there is a balance, let's say, between trying to be as generic as possible, but also thinking that if you look at some particular cases, you might end up with what you are looking for, let's say. And basically, the formation that I just mentioned is what typically people refer to as starving black hole. So you start with 10 to the 2 solar masses, let's say, you don't have a lot of gas, and at the end you end up with something that might be an intermediate mass black hole.
I have a question about direct collapse. So you mentioned that one source of UV radiation could be population 3 stars.
Yes.
But I assume that in those mini halos, most of the baryonic content is going for the direct collapse. So there might not be enough population 3 stars to collapse and generate that UV background.
I mean, you don't have POP3 stars from the same halo that produce heavy seeds, let's say.
Okay.
You have POP3 stars from the smaller halos.
Okay.
So, I mean, in principle, there are like 2 different sets of halos. So in principle, again, it depends on the relative abundance, but in principle, there might be enough UV coming from POP3 stars.
Okay.
Because you had enough like smaller, I mean, typically if you look like at the number density as function of mass, you see some sort of power law. So it's easier to produce something that is light than something that is heavy. You also find this in the initial mass function of the star, basically, that is the Krupa behavior. That's the same argument. So in principle, you have less heavy seeds black hole, and in that case, the UV radiation comes from the fact that you have, well, no, at this point there are primordial black holes there, but okay, that you have a lot of light seed and POP3 stars.
Okay. Thank you.
Okay, so now that we have kind of created our black hole, it's time to make them grow. And in principle, black holes can grow through 3 different processes, and each one of these processes has its like signature. So the first one, as you can imagine, is gas, and in this case, the observational probes is what we call AGN, that stands for active galactic nucleus. Again, about the nomenclature, people typically also call AGN QSO, that means quasi-stellar object. And that's because, well, originally when people observed the first massive black hole accreting, well, there was not yet the model of accretion around black hole. So basically what people were looking at was a very bright emission that was very localized. So it looked like a star, basically. So that's why originally they called quasi-stellar object. The second way to accrete is, of course, through mergers. And in this case, the signature that we have is, well, as you can imagine, gravitational waves. And the third way is stars. And in this case, the observational proofs that we have are TD, that stands for tidal disruption event. I think Elisa partially mentioned the idea of TDE. So I will focus mostly on gas and, as you can imagine, mergers. Just a quick comment on stars. The idea is that if you have a massive black hole and if you have a star that is orbiting sufficiently close to that, the stars gets tidally disrupted, just because the potential that the stars feels like at this point is different from the gravitational potential that the stars feels at the other point. And so, I mean, if you have seen like simulation, you end up with some sort of material that then can fall back on the black hole and again accrete it. So, but I will not focus on them. So let's focus on the gas, and to move on. Let's look at another quantity that is typically used in, again, astrophysics, and let's look at the Eddington limit. So here in this case, the situation is that imagine that you have a black hole well, sitting somewhere, and then you have again a cloud. In this case, we are gonna go for fully ionized hydrogen. Okay. And the idea in this case is that, well, some of the hydrogen will start collapsing, but as it collapses, it also releases radiation, basically, and this radiation will counteract the expansion. So now we want to look for the condition where we have some stability. Yeah, we can start deriving. So we can write that the typical flux is equal to the luminosity over 4 pi r squared, and this happens, of course, at a given distance r, okay, from the center. Well, I mean, I'm going to write it. I don't know if you already know it, but and where the luminosity can just be written as like the derivative of energy over time. So if you take the standard photon, its momentum can be written as E over C, which means that you can also write a momentum flux as basically the flux over C. So this is L over C 4 pi r squared. And the photon will, of course, act on the protons and electrons with a force. So we call it force radiation. That is going to be the momentum times the Thomson cross-section. So here we are considering things that are not relativistic. On the other side, you have the gravitational force, and again, the gravitational force in this case can be written just as G m r squared. And here, for example, you can write the mass of the electron plus the mass of the photons. And of course, like we neglect the mass of the electron. So the force acts mostly on protons. And at that point, what you can do is just you equate the two of them. So you equate these two. And if you do it solving for the L that you have over there, you end up with the expression of the Eddington luminosity. That is 4 pi G, mass of the proton times light, sigma T over M. And again, if we write this in more useful units, you end up with 1.26 times 10 to the 38 m over solar mass, and in unit of erg over second. So this type of luminosity is, as you can imagine, an approximation because it's basically, I mean, we derived this in the condition of spherical symmetry. If you are familiar with the idea of AGN disk, of course, this is not spherically symmetric, but typically it's considered like as a first-order approximation to have an idea of the typical luminosity of massive black hole. Well, actually of any black hole. And the idea is that, for example, if you plug a luminosity, if you plug a mass of 10 to the 8 solar mass, you end up with luminosity that is of the order of 10 to the 46 ergo per second. And just for reference, the typical luminosity of a Milky Way galaxy is 10 to the 44. So a typical black hole, massive black hole of 10 to the 8 is based at Eddington, accretes like, well, produce a luminosity that is 2 orders of magnitude larger than the Milky Way. Once we have defined this, we can also define some, well, we can also define in general the luminosity. Instead of writing it as d over dt, the idea is that, as I said, we have some material that is accreting on the black hole, so we can write the...
You said this Eddington luminosity is a limit, but I don't see why it's a limit.
Let's say that is the limit in like a very optimistic scenario, let's say, where you have like spherical symmetry and you are looking at the balance again between like the radiation that is pushing out and the matter that is trying to collapse. So in a sense, it's a limit, but okay, it's not, there is not a limit if you mean like limit for something that goes to zero, okay? But it's more like a conceptual limit because it's derived in very simplified assumptions. And with that, we can write the luminosity. I'm gonna rewrite this instead of d over dt. Now the idea is that we have some gas that is accreting, so we can write the luminosity as eta, the amount of matter that is accreted over c squared. So what this equation is telling you is basically that you have some mass that is accreting over a function of time, and this mass, this energy is computed with a given fraction in luminosity. So here it's basically, okay, let me rephrase. So this equation is completely generic in a sense that you can use this equation also to model your stars. Your physics enter in your definition of m dot accretion and on the definition of eta. So in this case, for a massive black hole, m dot accretion is the amount of gas that is falling, and eta, as we will see shortly, is the radiative efficiency that basically tells you how well you can convert the mass that is falling into black hole into radiation. But in principle, you know, you can just use this expression also to model stars. In this case, m dot accretion, you can just think as to the fraction of, to the quantity of hydrogen that is converted in luminosity due to nuclear reaction in a given time, and this eta becomes the efficiency of nuclear reaction. So just to say that this is generic, but your physics enter basically in these two quantities. So we can try to quantify a bit eta, so to have an idea of what is the typical radiative efficiency of gas falling into a black hole. So in this case, we consider a single black hole. Again, let's consider a gas element with mass m. And the idea is that we are looking at the energy that has been released from, let's say, infinity up to the inner edge of the circumbinary disk. So basically, again, first order approximation. Here we are going to use like Schwarzschild radius. Okay. So you can think that at infinity, basically the initial energy is 0. but when you're really close, but when you are basically close to the inner edge, your final energy is your binding energy. And this can be written as minus Gm over 2. And in this case, I'm putting R edge. So again, imagine that here there is the circumbinary disk, and I'm looking just at the edge, basically. So in this way, the typical difference that you have is, well, the difference between initial energy and the final energy is, well, as you can imagine, is the final energy itself. And if we consider the luminosity as d over dt, we can write this as g m dot m over 2 r edge, where this m dot has just become, where I applied the time derivative only to this small quantity of gas element that is falling. We can rewrite this. We can rewrite R edge as a factor beta. I'm going to show shortly what this beta is, times Schwarzschild radius. And if you just then replace R edge to this expression, you end up with a luminosity that can be written as 1 over 4 beta times m dot c squared. So in this case, you end up having your eta equal to 1 over 4 beta. So let's consider, for example, a black hole that is no spinning. Well, in this case, if you have like a Schwarzschild black hole, you know that the ISCO is at 6 Gm over c squared, which means that basically you have beta equal 3, which means that you end up with an accretion efficiency, with a radiative efficiency that is of the order of 0.08. On the other side, if you take something that is maximally spinning, you have that the ISCO, and you assume a prograde orbit, of course you have to distinguish between the two of them, you end up with Gm over c squared, so beta 1 alpha, and this brings you to eta equal to 0.5. If you do the full calculation in GR, you end up with a value that is 0.057 and 0.42. So, as you can see, even if we started from something that is very simple, at the end the results is not so different from what you have from a full GR calculation. Now we can also look at how much a black hole accretes. Because we have just defined that the luminosity is, we just defined the luminosity as eta m dot c squared. So the black hole on the other side grows as m dot equal to 1 minus theta m dot h. So basically the part of energy that is not emitted in radiation, as you can imagine, falls into black hole. So at the end you have just the 1 minus theta. So if you introduce another quantity that is a time scale that comes from the Eddington limit, so it's basically called the Eddington time, and it's basically mc squared over the Eddington luminosity. you end up, this quantity can be written as a sigma t c over, what is it? Okay. 4 pi g times the mass of the proton, so it's something of the order of 0.4 giga-year. You can write this expression basically as m dot equal to 1 minus eta f Eddington and m over t Eddington, where f Eddington is what people typically call Eddington ratio, and is the ratio between luminosity and Eddington luminosity. And you can see that basically you can integrate these equations. So here you have a dm over dt, here you have m, so you bring m on the denominator, t you bring on the other side, and if you do that, you end up with the expression that tells you how fast a black hole accrete, how fast a black hole grows in mass. So this is like m0, like the initial mass at time t0. And of course, this is an exponential function, so you have the exponential d of 1 minus eta f Eddington t minus t0 over, the Eddington. If we write this in more, again, it depends on the type of eta, but for example, if we assume that, actually I can just go. So if we assume that f Eddington is equal to 1, so if you're assuming that the black hole is accreting at Eddington, and if you take the case of A equals 0, so Schwarzschild black hole, you end up with an expression that is mt equal to m0 times e to the t of 3 times 10 to the 7 here. While on the other side, if you take a equal 1, you end up with an expression that is more like m0 e to the t of 3 times 10 to the 8. So what this is telling you? Let's try to compare these time scale.
Thanks. Sorry, I have some clarification questions about what you wrote on the right board. Like the R ISCO, the first one equals to, like, what is that thing before GM? On the lower right part of the board. Like A equals to 0, R ISCO equals to, what is that?
6 GM over C squared.
Okay, 6, okay.
It's just the standard expression for the ISCO for a Schwarzschild black hole.
Right, and like what's the full GR, the numbers in the bracket? What are they supposed to stand for? Like just like R ISCO, the value of R ISCO?
No, okay, I mean, if you do this, if you assume ISCO, you end up with a radiative efficiency computed in this simplified assumption of the order of 0.08.
Right.
Okay.
But if you don't use
if you do the full calculation in GR, you end up with 0.057.
I see, okay.
And the same here, basically. So what I wanted to say here is that you can get some intuition on the value of theta, even just applying some very simplifying assumption, and then you can compare it with full GR, and you see that it's actually not so bad. So we are doing some approximation, of course, in order to make things easier, but at the end, approximation are not so bad.
Okay, thank you. And sorry, like another clarification. So you wrote like on the bottom there, like L equals to 1 over 4 beta m dot c squared, right?
Yes.
And later on you wrote that expression where L is equal to eta m accretion dot c squared.
Yes.
Like, is it? But like, so you're just replacing m dot with m accretion dot? Then,
yes.
or?
Yes. Sorry. Okay, that was a mistake. Yes. Sorry for the notation, but yes, I was just replacing them.
Oh, okay. Wait, in that case, like, what do you mean that like m dot equals to like 1 minus eta m accretion? Like, is that like the first m dot? Is it like a different m dot? What you had?
So no, this is like the this is how fast the black hole accretes. So.
Okay.
Okay. So.
That's wait.
Okay. So the idea is that this expression tells you how much mass you radiate away. How much energy you radiate away. So the energy that is not radiated away falls into the black hole.
Yes.
So
okay. I see.
the black hole grows as just 1 minus theta times the rate of gas falling in.
Okay, thank you. I don't want to.
They are, okay.
Someone. Okay, I don't know.
You mean
don't need it.
Yeah, just
too small in sense of
yeah,
written?
yeah.
Ah, okay, sorry.
The exponents.
Okay.
Parce que c'est dur.
This is just T. The exponent is just T.
Fuck, so
And here you have. Okay.
Hi, quick intuition question. Can you give me a little idea of what exactly the Eddington timescale is and what that means physically? The 0.45 gigayears, I guess I'm trying to understand what's happening in that time frame.
Yes. I'm just going to replace them here, and we can
Okay,
we can see.
thanks.
There is,
No, I'm just surprised that in the A=1 case, when the gas is also co-rotating with the black hole, and we have assumed radial info in all the assumption we were doing, it's so similar to the eta. Just
Progiare.
yes. No, that was just a comment. Because I suppose, of course, you can also see, I think it's the A=1 case, the accretion is less efficient because the gas is co-rotating, I guess, in the MT equation.
Well,
Yes,
exactly. Technically, here we are not assuming the gas is co-rotating.
No, exactly. In the
We are,
Fourier, I
just
think, yes.
we are just assuming a radial infall, so it's not really co-rotating. It's just a different size where you stop looking at the gas, basically. I think that the difference of 0.08 is actually what you have taking into account a co-rotating system. Okay, so what this is telling us, so you know that the Hubble time is of the order of 1.4 times 10 to the 10 here. So what we can do is try to compare this type of evolution of mass with what we observe at high redshift. So you see that in principle, if you just take the Hubble time, you can have a E-fold factor of between 50 and 500, basically. So okay, I don't know if you are familiar with that, but typically people called E-folds the fact that basically is the power of this exponential, in the sense that if you have m equal to m0 to the power of 1, this corresponds at 1 E-fold. As you can imagine, if you have m equal to m0 e to the power of 2, then this corresponds to 2 E-fold. So if you read in the literature, you can see that people sometimes refer to this E-folds time, and is actually basically describing an exponential growth of your initial mass. So if you take the standard Hubble time, you can see that you have plenty of time to grow the massive black hole that we observe today, so at redshift 0, let's say. But what happens if you take the masses of black hole that we observe at high redshift? So the quasars, or AGN, again, that we observe at high redshift. And one example is...
They should have called it half-life or something.
Eh?
It should have been something like half-life. It's essentially, it feels like that, right? The inverse of the half-life is the E-fold.
It's growing, it's not done.
Yeah, no. As you go back in redshift, as you go into higher redshift, it's like you're Okay, never mind.
So, for example, at this moment, let's say the most massive AGN that has been detected is of the order of 10 to the 9 solar masses, and it's at redshift 7.4. If you take this redshift, this corresponds to a cosmic time of the order of 0.7 gigayear.
Sorry, can I ask you a question about the E-fold thing? So,
Yeah.
I mean, if I just plug naively like 10 to the 10 into the, let's say, spinning black hole case, so it looks like my black hole can grow by a factor of exponential of 100, right? So
Yes.
That's insane, no? It's like...
Accretion is very efficient indeed to grow black hole. And the problem here is that what I want to show here is that if you take this expression, you don't have a problem in explaining the massive black hole that is like at the center of our galaxy. That is not a problem. But what happens if you take like the AGN at high redshift? Because in that case, you are starting with something that, I mean, you're observing something that is very massive, but when the universe is very young. So the idea is that if you look at this and you assume this type of accretion, so very simplified accretion, can you explain the observation or not? And well, as you will see now, the idea is that sometimes yes, sometimes no, and it depends again on the efficiency basically. So it depends a bit on the spin. So for example, well, I'm not going to plug in numbers. I mean, you can do that, but for example, if you consider the case of non-spinning black hole, you can see that basically a black hole of 10 to the 9 solar masses might have grown of something of the order of 23. So wait, let me write it this way. So if A is equal 0, you might have 23 E-folds, which basically means that your initial mass can grow up to 10 to the 10. So this is basically telling you that you can start with like even a solar mass black hole, even something slightly below, and you can explain the observation in this case. However, for example, if you take something that is maximally spinning, then in this case you have just a couple of E-folds times, so 2.3. Which means that in this case, the original black hole, whatever it was, could have grown up to 10. So it means that if you want to explain this, assuming that A is equal 1, it means that you need a seed black hole of the order of 10 to the 8 solar mass, which is way too big. It's something that we know that we cannot create. So again, it's kind of a limit and kind of an approximation, of course. But the idea is that this type of techniques have been used to try to explain the observation at high redshift. Sometimes it works, sometimes it doesn't work, and again, it depends a bit on the cube over there. So sometimes it works, sometimes it doesn't work, and again, it depends on the spin and on your processes.
How do we observe this supermassive black hole at high redshift?
That's a good question, and I have prepared a section about the JWST observation for the next lecture, so attend the next one.
Thank you.
So these are ions that are potentially orbiting and falling in. We've ignored magnetic field effects.
Absolutely.
Is this not a very important effect, or is it like more of a additional correction term?
I mean, they affect the typical emission that you have from black hole. Like if you observe a radio jet, this is typically due to the presence of magnetic fields, because you need particles to accelerate and then to produce radio emission. But in principle, yes, you neglect them when you form black hole, like when you look at cosmological simulation, you neglect them because you assume that typically matter is neutral. The idea is that if you have something that is positively or negatively charged, immediately you have coming from some other part of the universe, something that is of the opposite sign, so you compensate. And also at the level of accretion, here, I mean, we are looking at timescales that are very long, so you typically neglect magnetic fields. They play a role when you are really close to merger. That's also something that I will mention like the next lecture, when we are going to look at things, I mean, when we are going to look at massive black hole binaries. But in principle, they play a role mostly at the end, let's say. Okay. How much time? Okay. Fair enough. Okay. So, as I said, we have derived all of these in like spherical geometry, but of course you know that well, this is not the case in general, let's say. So universe is not. I mean, when material is accreting on the black hole, it's typically form a disk. So I just would like to mention briefly what are disks and how we can model them. The subject is quite complicated, well, at least for me, because it requires a lot of, well, if you want to do things properly, you basically have to take into account viscosity, transfer of angular momentum from the inside to the outside. But a very simple model has been derived in 1973, and it's what we called Shakura-Tsunayev. And if you want well, I'm going to describe this quickly. If you want a proper explanation, for example, you can look at section 4.6 of a book that is called Accretion Power in Astrophysics. From J. Frank.
Sorry, did you say 4.6 or 5.6?
5.6. Okay, so the idea is relatively simple. The idea is that, again, you have a black hole. Imagine that you have a circumbinary disk. And the idea is that you look at the contribution that comes from each annulus. So the Shakura-Tsunayev is a solution for a disk that is that has some specific properties. So it must be steady state. So steady state, it means that its properties are not going to change in time. The idea is that you have, imagine that you have the disk, you have enough material that is like supplying the disk as much as material that is flowing inside the black hole. Actually, as much as enough matter falling inside the black hole. So your disk is at equilibrium. The other properties is that this is geometrically thin, which means that its height is much smaller than the radius. If you, I mean, imagine that you see this in projection, you basically have something that is very thin, because the idea is that in this case, the disk, I mean, if you are in this situation, the disk has indeed been flattened by the rotation, so you can actually disentangle some of the equations. So you can disentangle the equation that basically gives you the information along Z and the equation that gives you the information along R. And the second property is that it has to be optically thick. And optically thick means that radiation, well, photons in this case, are continuously absorbed and re-emitted inside the disk. So it's not like once they are produced, they can escape quickly, but they have a lot of interaction inside the disk, and then they can escape. If you assume this condition, you end up with what is called a black body spectrum. I guess you are familiar with that. You end up with a black body spectrum at each radius, basically. And the idea is that as you move like from inside to the outside, the peak of the black body will, of course, decrease. So here you will produce the most energetic photons. Here you will produce the least energetic photon. But since each radius emits as a black body, at the end you end up with a spectrum that is quite flat. And indeed, what we observe for AGN are typically flat spectrum. And this is indeed, for example, a strong difference with respect to what we observe for stars. Stars, we know that the spectrum is quite well described by a black body because, well, it's actually the same process of here. So photons are trapped inside the stars and it takes a lot of time to go out. Here it's kind of similar, but the idea is that you have multiple black body spectrum, so at the end you end up with something flat, and this is indeed what we observe for AGN. You can get also some idea of the temperature that we have. So the typical temperature of the typical temperature that depends on the mass and on the radius can be written as 2 times 10 to the 7 m over solar mass to the power of minus 1 over 4 r over Schwarzschild radius to the power of minus 3 over 4, and this in Kelvin. And you can and of course, I mean, let's just assume that r is equal to the Schwarzschild radius. And you can get some idea of what is the maximum energetic photons produced by a specific black hole. So, for example, if you take a black hole of 1 solar mass, you end up with the temperature at the inner edge, so again, Schwarzschild, of the order of 2 times 10 to the 7 Kelvin. This is X-ray. And indeed, before the LVK detection, basically, all the black holes that we have observed were X-ray binaries. There is a question there.
So I just wanted to verify. So does this mean that it doesn't necessarily depend on the spin of the black hole, like since that would get you a smaller inner radius on the disk?
No, it depends. It depends on the spin of the black hole. It depends on viscosity. It depends on many parameters. Okay. This is just a very simplified model.
Thank you.
Yes, actually, I mean, in principle, for example, as I said, here we are assuming like steady state. So we are assuming that the disk is stable. Mm-hmm. For example, if you take simulation of massive black hole binary when they are close to merger, you can see that this picture completely drops. I mean, this assumption is not anymore valid. Here is just considering the standard massive black hole, let's say. On the other hand, for example, if you assume a mass of the order of 10 to the 7 solar mass, you end up with the maximum temperature of the order of 3 times 10 to the 5 Kelvin. Which brings you to UV band. So this tells you that the maximum energy of the photons that you can produce from a massive black hole is basically in the UV band. However, this is not the end of the story, because in principle from very massive black hole, we can also observe X-ray, for example. Where does the X-ray emission come from in the case of massive black hole? Here we enter a topic that again, I'm just going to mention it quickly. But we enter a topic that it has been studied a lot in the literature, but it's, in a sense, it's complicated and still uncertain. But I'm just going to mention you, so I just want to mention this to you so you are aware of this possibility. So the idea is that imagine that, again, you have your massive black hole, you have your disk that is indeed producing photons. The idea is that below and above the black hole, there is a region that people typically call black hole corona. So the things that we know so far about the black hole corona is that it's a region that is very compact, basically the same size, well, maybe 1 order of magnitude larger than the Schwarzschild radius, but it's poorly constrained. We know that it's there because the idea is that this is the region responsible for producing the X-ray emission. How? With a process that is called inverse Compton scattering. So the idea of the inverse is, the word inverse comes from the fact that what we are scattering here are basically UV photons against electrons. Electrons that are energetic, so the electrons are much more energetic than the photons. And these produce, indeed, what is called inverse Compton scattering. So the idea is that since the electrons are more energetic than the photons, the electrons end up giving some energy to the photons. And in this way, you go from UV radiation that comes from this area to X-ray radiation. If you look in the literature, there are plenty of papers about coronae. It's actually a region that has never been resolved because you really need a very high resolution in order to resolve this area. What we are seeing is that there is some X-ray emission, and this is one of the, I think at this point, it's the universally accepted explanation to indeed explain the X-ray emission from massive black hole binaries. Because otherwise, as we have seen, the temperature is not high enough.
So the electron absorbs heat and then re-emits X-ray and then goes to a very safe point.
I think it's just Compton scattering, so it's just absorbing, in principle, you can think that it absorbs, then you have a charge that is accelerating, and then it emits again. Yes, it's the same way. Yes, exactly. No, it does. Technically, you have some continual replenishment of this electron in this area. Where do they come from? That is not clear to me, honestly, and maybe I think it's not clear even to the people that work on that. For sure, you have some contribution from the disk. The idea is that they can stay here also because there are magnetic fields. I've not mentioned them and not going to treat them, but in principle, there are magnetic fields that can trap electron in a very small region. If you have your line of magnetic fields that are very collimated, basically you know that the electron will stay around here. But yes, that's the general idea. But as I said, it's something that of course with years it's getting better and better, but I would say that it's still poorly constrained case.
You said this is for massive black hole binaries, but...
Sorry, massive black hole.
Okay.
Sorry.
And we observed also binaries with this property, of X-ray emitting or UV emitting sources.
Well, the idea is that the stellar mass black hole that we have observed so far without LVK they all come from X-ray binaries. So in that case, is that the idea is that you have a black hole, you have some donor star that can be like a main sequence star, white dwarf, pick your models, and the idea is that materials start falling into the black hole. This is for stellar. For massive, as I will say in the next lecture, we have no observational evidence of any electromagnetic counterpart at the moment. Or, let's put in another way, maybe there is some sort of, maybe we have observed already the electromagnetic counterpart from a massive black hole binaries, but we are not able to recognize that. So this brings, well, okay, I think, okay, just last thing and then I will close. This brings us to the final idea of feedback, in the sense that, well, basically this picture works let's say that works up to a certain point, in the sense that we have seen that indeed if you have a massive black hole and if you have some gas falling in it, the idea is that it starts accreting, but it also produces radiation, and this radiation, as we have seen, basically push back the gas. So this produces what is typically called a feedback mechanism. And this feedback mechanism is a way to self-regulate the growth and the electromagnetic emission of a massive black hole. And the idea is that you have some gas that is accreted. Then, if gas is accreted, then radiation is produced. This radiation acts back on the gas, so the gas stops accreting. And if the gas stops accreting, the massive black hole becomes quiescent. And at this point, since it becomes quiescent, it can start again accreting gas. What? What? It's not accreting like dormant. That is just sitting there without gas around it. So this is like a self-regulating mechanism that indeed regulates the mass of the black hole. Okay. That indeed regulates the mass of the black hole along cosmic history. It's something that has been observed a lot, and actually, I mean, we can compare our prediction with our model, and indeed we see that this picture generally holds.
Sorry, what do you mean by we observed a lot? Like, we observed black hole stop accreting and then start, like, yeah, what do you mean by this?
So something that you can do, and I didn't have time to do that, is to look at the Soltan's argument. So Soltan's argument basically tells you that the mass density of black hole that you observe can be explained directly with accretion. So basically, you're comparing the mass density of black hole with the luminosity density, with the function of luminosity, the luminosity distribution of massive black hole, and you can see that the two agree.
So you don't observe, like you don't look at a black hole and look at, like you can't see change with time, right? But you can look at the distribution and then infer that this feedback mechanism is a thing?
Yes. So, wait. So first of all, yes, you can observe variability in AGN. Few days.
AGN, okay, yeah.
In few days, you have variability of AGN. But of course, this is like few days, so it's very limited time scale. This feedback mechanism takes place, I mean, over mega years, so it's like more a cosmological time scale. Okay. Okay.
Another question. You are talking here about massive black holes, so does this work for intermediate mass black holes as well? All this mechanism, accretion, and everything? Like, all of the theory which we have described here, and like all the radiation which is being produced, like the X-ray, UV band, and all of that. So you just mentioned the fact that it's all about massive black holes, but does it also work for intermediate mass black holes, and can we have EM signatures described via these processes for them?
Okay. In principle, yes. So there is nothing that prevents you to have something very similar. Again, maybe, okay, if you take an intermediate mass black hole and if you assume that it's in the center of galaxy, and if you assume that you are observing it like today, redshift 0, redshift 2, then it means that it has not grown much. So in principle, you can call this sort of mechanism, of course, but you expect not to have a lot of gas, let's say, because you are already observing something that is intermediate mass, like 10 to the 3, 10 to the 4, 10 to the 3, 10 to the 4 solar mass is very close to us. If you move the picture of the intermediate mass black hole to the idea of globular clusters, like when they are in clusters, then situation is a bit more complicated in the sense that since you have a lot of stars and black hole, gas is way much hotter, basically, than what you typically have around the circumbinary disk of massive black hole binaries. And in that case, I think that this picture, it doesn't really happen anymore. It doesn't hold anymore because at that point, your evolution is determined more by the dynamical interaction between the object in the cluster rather from the quantity of gas that is accreted. You might have some accretion. I think there has been some paper in the literature, but I have to check honestly. You can have some accretion, but this I will not call this mechanism as the one dominating the growth of an intermediate mass black hole sitting in the center of a globular cluster. And I think that with that for today, we are done. Thank you very much, Alberto. Are there final questions? Or maybe, we can have a break and reconvene in 15 minutes. So the next lecture for you is on Thursday afternoon? Afternoon. Yeah. Okay. Thank you again.